Have you ever stood at the base of a massive skyscraper, looked up, and just wondered, how on earth does this thing stay standing? It feels like a miracle of modern engineering, right? Well, today we're going to pull back the curtain on one of the most crucial yet surprisingly simple tests that makes these towering giants possible. It's a foundational step that every single skyscraper, from the Empire State Building to the Burj Khalifa, has to pass. Stick around, because what you're about to learn will completely change how you look at the cities around you. Before a single steel beam is erected, before the first drop of concrete is poured, there's a question that keeps engineers and architects up at night. What's underneath? You see, you can design the most incredible gravity-defying structure in the world, but if the ground it's sitting on can't support it, it's all just a very expensive, very dangerous blueprint. The ground beneath our feet isn't a uniform solid block. It's a complex layer cake of soil, clay, sand, gravel, and rock, all with different properties. Some layers are strong and stable, others are soft and squishy. Building a million-ton skyscraper on the wrong spot is like building a castle on quicksand. So how do they figure it out? This brings us to the star of our show, the soil test. I know it might not sound as glamorous as welding steel at 2,000 feet, but trust me, it's where the real magic begins. The most fundamental and widely used method is called a borehole test. Imagine a giant, hollow drill, like an apple corer for the earth. Engineers drill deep into the ground at the proposed construction site, sometimes hundreds of feet down, well below the foundation level. As the drill goes down, it collects cylindrical samples of the earth at various depths. These samples are called soil cores. Each core is a perfect cross-section, a story of the ground's history, showing every distinct layer. These cores are carefully extracted, labeled with their exact depth, and sealed to preserve their natural moisture content. Then, they're taken to a geotechnical lab for a series of intense examinations. It's like a full medical checkup, but for dirt. Scientists will analyze the type of soil. Is it sandy, clayey, or silty? They'll measure its density and moisture content. They'll subject the samples to immense pressure to see how much weight they can bear before they compress or fail. This is called the bearing capacity test, and it's the single most important piece of data they're looking for. It tells the engineers exactly how much load the ground can safely handle per square foot. Think about it this way. A skyscraper doesn't just push straight down. It exerts an incredible, concentrated force on a relatively small patch of land. The results from these soil tests dictate everything about the skyscraper's foundation. If the ground is super strong, like solid bedrock close to the surface, they might use a simpler, shallower foundation. This is the dream scenario, but it's pretty rare in a lot of major cities like Chicago or London, which are built on softer clay and silt. So what happens when the ground is weak? This is where engineering gets really clever. If the tests reveal soft soil, engineers have to design a deep foundation system. This usually involves driving huge concrete or steel piles deep into the earth, sometimes hundreds of feet down, until they hit a solid layer of bedrock or a very dense layer of soil that can take the load. The skyscraper then essentially stands on these stilts. The entire weight of the building is transferred through the piles, bypassing the weak upper layers of soil and resting securely on the strong stratum deep below. The number, size, and depth of these piles are all determined by the data from those initial borehole tests. Another crucial piece of information they get from these tests is about groundwater. They'll measure the water table level and understand how water moves through the soil. Why does this matter? Well, water can weaken soil, and a high water table can exert upward pressure on a foundation. It also means construction crews might have to do extensive dewatering of the site before they can even start digging the foundation, which adds a lot of complexity and cost to the project. The soil test prepares them for this, so there are no surprises. Let's take the Burj Khalifa in Dubai, the tallest building in the world. It's built on a challenging mix of loose sand and weak sedimentary rock. The soil tests were absolutely paramount. Based on the results, they engineered a massive foundation consisting of 192 concrete piles, each about 5 feet in diameter, drilled over 164 feet deep into the ground. The building's weight is transferred through these piles to the more stable rock layers far below the surface. Without the precise data from the soil tests, a project of that scale would have been impossible. It's the unseen hero of the Dubai skyline. And it's not just a one-time thing. For a huge project, they won't just drill one borehole. They'll drill dozens, creating a detailed 3D map of the subsurface geology across the entire site. This helps them identify any inconsistencies. Maybe one corner of the site is weaker than the other. This information allows them to customize the foundation design, ensuring that the building will settle evenly and won't tilt over time. Yes, buildings do settle a tiny bit after construction, and the goal is to make sure that settlement is uniform. The Leaning Tower of Pisa is the world's most famous example of what happens when you get the foundation wrong because of inadequate understanding of the soil beneath. So the next time you find yourself marveling at a skyscraper, remember that its incredible height is only possible because of what lies hidden deep beneath the ground. It's a testament to that simple yet profoundly important first step. Drilling a hole in the ground to ask the earth, "Are you strong enough?" The answer they get from that core sample is the true foundation upon which all of our modern vertical cities are built. It's the silent, invisible science that keeps our skylines reaching for the clouds. Thank you so much for joining me on this deep dive into the world of construction. If you found this as fascinating as I do, please hit that like button and subscribe for more peeks behind the scenes of how our world is built. Let me know in the comments what other engineering marvels you'd like to learn about. Until next time, stay curious.